The electron is a subatomic particle with a radius of 2.8 times 10 to the negative 15 meter. That's 0.0000, you get the point. Smaller than the tip of your finger, smaller than the cells on the tip of your finger, smaller than the atom that makes up the cells. Something so small couldn't possibly affect you, right?
Wrong! Electrons and their configuration determine how all the atoms in the universe interact with each other. Every single chemical reaction is the work of electrons, so pay attention and learn how this tiny particle controls your life.
Electrons are subatomic particles that cannot be divided by natural means. They were discovered by J.J. Thomson in 1897. Using his cathode ray tube experiment, Thomson was able to measure the charge and the mass of an electron. These values have been refined over time, and today we accept that it's 5.486 times 10 to the negative 4 AMU as the mass of an electron, and 1.602 times 10 to the negative 19 coulombs as the charge of an electron. No one ever needs to know the charge of a single electron, so its electrical charge is more commonly expressed as Faraday's constant. Recall that Faraday's constant is 96,485 coulombs per mole. This expression is named after Michael Faraday, a prominent chemist in the 19th century.
Another important scientist in the 19th century was John Newlands. In 1865, John Newlands recognized that certain elements had similar characteristics. He theorized the law of octaves, which states that if the chemical elements are arranged according to their relative atomic weight, every eighth element will have comparable physical and chemical properties. Newland's work helped Mendeleev develop the periodic table, in which each family of elements has similar traits. These advances helped other scientists create new models.
In 1913, Danish physicist Niels Bohr developed a new model of an atom which depicted a small positively charged nucleus surrounded by electrons, in what later became known as the Bohr model. Electrons orbited around the central nucleus. As the atomic number of the element increases, the number of protons and electrons in the atom also increases. The electrons formed shells around the nucleus, each with a different energy level. The greater the number of orbits, the higher the energy level of the furthest orbit. The electrons in the furthest orbit are called valence electrons.
Although John Newlands didn't know it, the trend he identified was possible because of valence electrons. Valence electrons allow atoms to react with other atoms, so the elements with similar chemical properties generally have the same number of valence electrons. The octet rule states that in general, the atom is most stable when there are 8 valence electrons, and that the atom will continuously seek this condition by adding electrons, losing electrons, or bonding with other atoms. There are a few exceptions to this rule, such as BH3 and PCl5. Elements that often have less than 8 electrons include boron and beryllium. BH3, for example, is stable with only 6 valence electrons. There are elements such as sulfur and phosphorus that can exist with more than 8 electrons, such as the phosphorus in PCl5.
When energy is added to valence electrons, they can jump from lower energy orbit to a higher energy orbit. However, the higher energy level is unstable and eventually the electrons fall back down to its original energy level. Although Bohr was correct in many aspects, further research has revealed that he was incorrect in assuming electrons moved around the nucleus in a perfect circular rotation.
The Heisenberg uncertainty principle states that it is impossible to determine the exact location of an electron. This is because the light particles we use to find the electron would affect its position. In other words, we cannot see the electron without also moving it. We can, however, predict the general location of the electron. The general location of the electron is described with orbitals. Orbitals are categorized into 4 subsets: S, P, D, and F. Each can hold different amounts of electrons. S orbitals can contain up to 2 electrons, P up to 6, D up to 10, and F up to 14. To better visualize these orbitals, we use orbital diagrams. In order to make an orbital diagram, you must follow these laws.
The off-balance principle states that electrons must fill in the lowest energy orbital available. For example, 1s will be filled before 2s, and 2s will be filled before 2p. The order of energy is S, P, D, then F. The next law is the Pauli exclusion principle, which declares that the maximum of 2 electrons can occupy a single orbital, and that they must spin in the opposite directions. For example, there cannot be 3 electrons in one single orbital. The last of the laws is Hund's rule. Hund's rule says that electrons must occupy all orbitals equally before pairing up in other orbitals. For example, if you have 7 electrons, the last 3 electrons must spread evenly across the 2p orbital.
But drawing all those arrows is time-consuming and inefficient, and we are really lazy people. That's why we have standard notation. Standard notation of electron configurations look like this. To write these notations correctly, you must write the energy level, followed by the orbital. In superscript, write the number of electrons in each orbital. Repeat this for each energy level and orbital until you have accounted for all the electrons. But if you're even lazier than that, you can write the electron configuration using noble gas notation. Noble gas notation looks like this, and is identical to standard notation, except that most of the configuration is replaced by a noble gas in brackets. The brackets represent the electron configuration of the noble gas, which should be identical to the part of the writing you replace. The noble gas configuration allows scientists to clearly discern how many valence electrons the element has.
Unfortunately, the valence electrons don't always stay in the orbitals you expect them to stay in. To accommodate bonds with other atoms, electrons sometimes form hybridized orbitals. Atoms need unpaired electrons to form bonds, which it may not always have in its ground state. The C in CH4, for example, has an electron configuration of 1s2, 2s2, 2p2, and only 2 unpaired electrons. To bond with the 4 hydrogen atoms, C needs 4 unpaired electrons, so it borrows an electron from the 2s orbital. By using electrons from both the 2s and 2p orbitals, the atom forms 4 sp3 orbitals, each containing an unpaired electron. To determine the type of hybridized orbitals that is formed, count the number of bonds on lone pairs. If there are 2, the hybridized orbitals are sp, 3 sp2, and 4 sp3. For atoms which don't follow the octet rule, the hybridized orbital can include electrons from the d orbital. 5 bonds in lone pairs result in sp3d orbitals, while 6 result in sp3d2 orbitals. Atoms rarely have more than 6 bonds and lone pairs, so don't worry about those.
As electrons jump from orbital to orbital, they absorb or release energy called quanta. The energy is the difference between the 2 orbitals' energy levels, and takes the form of photons. Each element will give off a specific set of light frequencies, allowing scientists to determine the element through atomic emission spectroscopy. We will now demonstrate how to use flame emission spectroscopy.
For this example, we are going to make green fire. Green fire can typically be made by mixing 2 chemicals. Those chemicals are boric acid and methyl alcohol. To make green fire, you need boric acid, commonly found in roach killers, methyl acid, which is found in heat and antifreeze. You will also need stoneware or metal container, lighter, measuring cups and measuring spoons, and a stirring stick. For safety, you should wear gloves to keep chemicals off your hands, and also wear safety goggles to protect your eyes. If you have a fire extinguisher, that would be best, but in this case, I just use a bucket of water. First step is to pour the methyl alcohol into the metalware. In this example, I use 1/2 cup. The second step is to add the boric acid into the methyl alcohol in the metalware. In this example, I use 2 teaspoons. The third step is to mix together the boric acid and the methyl alcohol by using a stirring stick. At the end, most of the boric acid should be dissolved, but if some is left on the bottom, it's fine. All that's left to do now is light it up. I moved to a darker place and lit it using a piece of paper just to stay safe. That's all you need to make a green fire.
So hopefully you've gained an appreciation for all the electron does for you. If not, just know the electron is responsible for all this cool stuff.